Okay, hey everybody, this is the supplemental video for my on-campus stats. Uh, we'll be talking about the five-number summary and box plots and some Excel computations for outliers. That'll wrap up our discussions from chapter 3. And then we'll be continuing on with the PowerPoint for chapter 4, part 1. Okay, so from chapter 3 and section 3.3, we looked at measures of relative standing. So looking at each individual data point and determining something like maybe where does it stand relative to the other data points in the data set. And one of the things that we saw was important is our discussion of skewedness and outliers. And related to that idea, we had developed percentiles and quartiles and the IQR method and so on. And we have one more descriptive statistic that we are going to talk about, the five-number summary, really kind of a collection of descriptive statistics, along with a graphical representation of that summary. And this is a pretty simple idea. The five-number summary is the list of these five numbers, the minimum of the data set, Q1, the first quartile, the 25th percentile, the median, the 50th percentile of the data set, Q3, and the max of the data set. So for example, if we had the Ashley data 5, 7, 8, 9, 11, we see that to find our quartiles and so on, we need to find percentiles. Let's set up our chart, 0 to 100%. We need 5 equal size bins, and that's at 20, 40, 60, and 80%. And the data points in each of these bins, 5, 7, 8, 9, and 11. So my five-number summary, these five numbers that I might give to represent the Ashley data, actually, it's kind of funny. It turns out that Q1, the 25th percentile, is 7, and Q3 is 9. The median, the 50th percentile, is 8, and the min and the max, 5 and 11. So it actually turns out that if our data set has 5 data points with different data values, then our five-number summary is actually just those 5 numbers. Of course, typically we would be working with samples or populations that are much bigger than an N of 5. So in that case, in those cases, this would be a more meaningful descriptive statistic. And here in these examples, it's just a little funny how it works out because we're using fairly small data sets to work with. So why report a five-number summary? Well, this gives us an idea of the middle of the distribution. It gives us an idea of the typical spread of the distribution, something like a measure of variation, Q1 to Q3, 7 to 9. So we might be able to say like a typical day for Ashley looks like 8 returns per day, and kind of a typical spread, something akin to a standard deviation, is 9 minus 7, or 2 returns per day. And then we list the min and the max just to show kind of the total spread of the data set. What's the lowest value and the highest value that we actually observe in the data set, 5 and 11. Now, one little caveat to this is sometimes the min is reported as the minimum non-outlier, and the max is sometimes reported as the max non-outlier. In other words, what we may do in some cases, what some folks may do when they report the five-number summary, they may first make a pass through the data, use something like the 1.5 IQR method, find any outliers, and then kind of remove those outliers from consideration when reporting, say, the min and the max. And again, this is just kind of a different perspective. It's just going to give you a slightly different descriptive statistic or set of statistics that are being reported. And as long as that's made clear, it's not that that's, you know, necessarily good or bad, or that one is better than the other. It's just a different set of statistics that's being reported. We might be interested in getting a graphical representation of this 5-number summary. And the way that we would do that is we would first draw a line. This is representing the real line. On this line, we want to indicate 5 positions, these 5 numbers in the 5-number summary. I'll just use actual min and actual max, not the min and max non-outliers. But I would want to record the position of the min. Let me give myself a little more room. The min of 5, the Q1 of 7, the median of 8, Q3 of 9, and the max of 11. And what I'm going to do is I'm going to draw my box plot, my graphical representation above this real line, just kind of in this empty space up here. So I'm just going to draw a vertical tick mark above the min, Q1, median, Q3, and the max. And this is called a box plot, or sometimes it's called a box and whisker plot. I'm going to take my middle 3 tick marks and I'm going to just connect them together like this to make a box. And then from my left side, going Q1 down to the min, I will draw a single horizontal line, sometimes called a whisker. And then same thing going from Q3 to the max over here. So this is our box and whisker plot, or just box plot. It's a graphical representation of the 5-number summary. And something I can tell pretty quickly looking at this, I see that the whiskers look pretty even. The median kind of appears to be roughly in the middle between Q1 and Q3. That's, in this case, is exactly in the middle. But this just kind of suggests to me that I have a nice symmetric distribution. If I instead saw maybe a median, say over here, and maybe a right whisker that was much longer than the left whisker, maybe that would suggest to me maybe some right skewedness. Or if I saw a median kind of nicely in the middle of Q1 and Q3, but I saw whiskers that were very long relative to the width of the box. Remember, the width of this box is an IQR, and it certainly looks like the right whisker is more than 1.5 IQRs away from Q3, and similarly for the left whisker, maybe this is symmetric data, or maybe not quite enough evidence to call it skewed, but it certainly looks like there are some outliers here because of the size of the whiskers relative to the size of the box. Now, one thing that I want to mention about this is, just like up here, there's kind of 2 ways to interpret min and max. Sometimes, and the way that I do it, is just to say the actual min and max. But some folks will go through and kind of call out the outliers first, and their min and max that they report will be the min non-outlier and the max non-outlier. For the folks that take that approach, they could make a 5-number summary with the non-outlier min and max, set up the box and whisker the same way, and then sometimes what they'll do is they'll indicate the outliers themselves by dots. So this has the benefit of you actually see the outliers. You know, this is a very different picture from, say, one that looks like this. Right? Although the box and whisker plot in those 2 scenarios, where we have a bunch of outliers on the right, or maybe only one, the box and whisker plot with just using the actual min and max wouldn't pick that up because the whiskers would just extend all the way out. But, pointing out each of those outliers with a dot maybe is a preferable way to go for some circumstances. So that's another type of box and whisker plot you might see is the box and whiskers. The whiskers only going to the min and max non-outlier, and then the outliers being individually indicated with points. So in this case, we would see that there are 3 outliers, and people were usually going to use the 1.5 IQR method for finding these outliers. So there are 3 outliers under the 1.5 IQR method, and in this picture, and my box and whisker plot tells me a little bit about the non-outlier values. Okay, so that is the 5-number summary and box plot. Again, pretty easy to compute. There's not really much new as far as computations here. This is just combining statistics that we've talked about already. And then this graphical technique of making the box plot is a pretty straightforward graphical technique just based off that 5-number summary idea. Okay, and then there's one last thing that I want to do in section 3.3 is jump over to Excel and run through a couple Excel computations for outliers. We'll just look at some data sets in Excel, go through the different methods of detecting outliers that we had talked about, and use Excel to help us with a little bit of the calculation. So there we go. We've got Excel up. And this Excel spreadsheet, this is the one that we've been working with the Ashley, Brandon, and salary data. This should look pretty familiar. If we go to the tabs down here, there's a tab outlier data sets, and that's what I'm working in right now. So the first data set we have is the Challenger mission flight times in minutes. And if we look at these, we see that there's kind of an obvious outlier. I think just about anybody looking at this data set would call this an outlier. Do we pick that up in the things like seeing some left skewedness or the 2 standard deviation test or the 1.5 IQR test? Let's see how this all parses out. This is obviously the Challenger mission where the shuttle blew up, shortly after it took off. I think we would all call this an outlier. Let's just see what we end up with over here. Well, first, let's give the data set a name. I'll just call it Challenger. I don't really care if it's a bit of a long name. I can use autocomplete. It makes it pretty quick. If I call this a sample, stdev.s of Challenger, the range is the max minus the min. The mid-range is the average of the max and the min. So I want max plus min over 2, but max plus min has to be in parentheses. So max plus min, I open the parentheses, I need to close the parentheses, and then over 2 for my mid-range. My mean, average of Challenger, and median equals median of Challenger. So I do note that my mid-range is less than the mean, and the mean is less than the median. My mid-range is about 6,000 relative to a mean of 9,000. That's about 30% difference or so. The mid-range will be about 30% below the mean. The mean to the median is about 1,000 units on a scale of 9 or 10,000, so that's about a 10% difference. Is that enough of a difference for us to call it skewed or not? We might be a little hesitant, right? We might say, maybe the 30% looks good, but the 10%, is that enough? 10% difference between the mean and the median, is that enough or not? Is that enough for us to say that that's a big difference? Well, let's go with something more objective. Let's go with the Pearson coefficient. 3 times mean minus median over standard deviation. And remember, the Pearson coefficient we're comparing to plus or minus 1. So if the Pearson coefficient was less than -1, we would say there's evidence of left skewedness. Negative 0.95 is awful close to -1, right? If we were being completely objective, we would say there's lack of evidence of skewedness because this falls between -1 and 1. But qualitatively speaking, if we're, if we're thinking about this, if we're using our brains, we say, well, that's awful close to -1. It does look like there's an outlier on the left here, not balanced by a right outlier. I'm still pretty suspicious of left skewedness, of this being an outlier, right? I might qualitatively make a judgment here to report something like, say, the median is a typical data point rather than the mean. Maybe I would think that that's a better measure to report in light of the Pearson coefficient being so close to -1, right? Maybe I would make that qualitative judgment. The two standard deviation test, we take the mean minus 2 standard deviations for the lower bound and the mean plus 2 standard deviations for the upper bound. Do I have any data points with value bigger than 15,905? No, the largest data value is 11,800 or so. But on the lower end, 7224 is not an outlier, but 1 is clearly an outlier. It falls below 2,000 or so. So the two standard deviation test does indicate 1 as being an outlier. For my 1.5 IQR method, I have to compute the quartiles first. I don't want to use Excel's built-in function. I know that that kind of computes percentiles a little different than we did it in class. But I note that there are 10 data points here. So these 5 and 5 more. I could use count if I had a bigger data set. Equals count of challenger is going to tell me how many data points there are. If I had, 100 data points or something, I might want to do this, but here I could pretty easily see it's 10. So if I just imagine the interval from 0 to 100% being cut up into 10 equal intervals, I'm going to have my breakpoints at 0 to 10%, 10 to 20%, 20 to 30%. 8709 is going to live in the 20 to 30% bin. That's where Q1 is. The third from the bottom is going to be Q1. The third from the top is going to be Q3 by symmetry. And we can check that. We know that the highest value, the data point with the highest value is going to live between 90 and 100%, 80 to 90%, 70 to 80%, and 75% falls in that bin as we expected. So Q1 is going to be that number. And Q3 is going to be that number. What's an IQR? It is Q3 minus Q1. And if I have 1.5 IQR, it's 1.5 of those. So we're going to go 4,000 units to the right of Q3 and to the left of Q1. And those are going to be our kind of normal data values, our non-outlier data values. So I want Q1 minus 1.5 IQRs for the lower bound. And I want Q3 plus 1.5 IQRs for the upper bound. I get an upper bound that's about 15,000 or so. Again, I see no positive outliers. I get a lower bound of about 4,600. And again, I see that 1 is the outlier. Something that I noticed, though, is the presence of this outlier. What has it done? It's brought the mean down by 1,000 units or so. And it likely has drastically increased the standard deviation. If this number 1 was something like, let's say 5,000 instead, what happens to the standard deviation? It goes from 3,500 to 2,000, right? It gets cut nearly in half just on the basis of that one data point. If I brought this up to something like 8,000, putting it kind of in the middle of the data here, I see my standard deviation gets cut even further, right? This outlier down here has a huge effect on the standard deviation and also pulls the mean in the direction of the outlier. We see that coming up in our true standard deviation test. The lower bound for the true standard deviation test, searching for low outliers, is 2,000, where for the 1.5 IQR is 4,000, 4,600. So for instance, if this 7224 were instead, let's say 3,000, well, now we have our lower bound for the true standard deviation test chasing that left side where these, I mean, I think most people would look at 3,000 relative to numbers from that are mostly all from say 9 to 11,000. I think most people would call this an outlier. We see our true standard deviation test, this lower bound is just chasing those outliers because it's bumping that standard deviation way up in the presence of those outliers and pulling the mean in the direction of the outliers. And the 1.5 IQR test is completely unfazed by this new 3,000, or if I change that outlier of 1, right? My two standard deviation test is heavily affected by those outliers, but my 1.5 IQR method not affected at all. That 4,605 was the same, even when I changed this to 3,000, right? So in this case, both methods come up with the same qualitative conclusion that the data point with value 1 is the only outlier, but we can clearly see that difference in robustness between the two. Okay, so let's look at this data, crash head injury criterion. So this would be like, you know, somebody sets up a car with crash test dummies, they crash it into a wall, and the crash test dummy has a sensor in its head deciding, you know, what are the forces and accelerations and things going on. And obviously, the higher the forces, the more likely a person who would be in a similar crash is to be injured. So that's what these numbers are kind of representing. So let's go through and do the same process on these numbers. So let's look at, well, first let's give this a name. Let's just call it HIC. HIC. That'll be our data set, head injury criterion, HIC. I'm going to do stdev.s of HIC. For range, I need max minus min. Maybe I'll do a max and a min down here so that I can just reuse these. So for range, I need max minus min. And for mid-range, max plus min over 2. What's the mean, average of HIC, and the median? I see my 3 measures of center. Well, the mid-range is higher than the mean, and the mean is higher than the median. This is how the measures of center would line up if I had some right skewedness. But is 435 really a lot bigger than 430? Is 430 really a lot bigger than 393? You know, we have something like maybe a 10% difference between these, but a really minuscule difference between the mid-range and the mean. So again, my measures of center, kind of unclear, right? It would be a pretty subjective judgment if I was just looking at those. Let's loop the Pearson coefficient in. 3 times mean minus median over standard deviation. And my Pearson coefficient turns out to be positive 1.25, indicating some right skewedness. I'm a little skeptical of this because if I was really right skewed, I'd expect mid-range to actually be the most affected of these, right? I would expect the mid-range to be really far away from the mean, even further than the mean is away from the median, right? that was kind of the structure that we saw up here. The mid-range to the mean was like 30 or 50% difference, depending on which one you take as the basis. But the mean to the median was only about 10% difference. So I look at this and I say, this is a little strange that the Pearson coefficient is indicating right skewedness, and but I really don't see that with the mid-range relative to the mean. So let's take a look at outliers. Do we see a right outlier? If we see a clear right outlier and no left outliers, maybe that tilts us in the favor of saying, okay, let's call it right skewed and let's be careful and report something like a median rather than a mean. If I don't find any right outliers, maybe I'm a little less confident with that. Maybe I think that, okay, this Pearson coefficient is completely objective, but maybe it's a bit spurious in this case, maybe leading me down the wrong path. Just because a measure is completely objective doesn't mean that it's that it always leads you to the right qualitative conclusions. So let's do the two standard deviation test. So I have mean minus twice standard deviation and mean plus twice the standard deviation for the upper bound. Do I have any data points with value less than 252? No. Or bigger than 607? No. So the two standard deviation test would say no outliers. Okay, let's look at the IQR test. We know that the two standard deviation test has some flaws, in particular that if we had outliers, it would bump the standard deviation way up, maybe pull the mean towards those outliers, and it makes it a little less, it makes the test's ability to detect outliers a little less robust. Okay, so I need Q1 and Q3. I have 7 data points. I need to divide the real line from 0 to 100% into 7 bins. Let me switch my share back over to OneNote, and we'll do that just a second over here. So now I need zero to 100. These are all in just percent. I need to split it into 7 equal size bins. So I need 6 tick marks. I note that 0 is 0/7 and 100 is 7/7. And I really only need Q1 and Q3, so I don't need to go until I find the 25th and 75th percentile. So 1/7 is about 14%. 2/7 is about 28% or 29%. So I see Q1 is going to be the second from the bottom, which means Q3 is the second from the top. As kind of a side note, the sevenths are kind of interesting. 1/7 is 0.142857 repeating. Note that like 14 doubled is 28 and 28 doubled is 56, which is like almost 57. 2/7 is 0.285714 repeating. And the sevenths just kind of, they cycle around these 6 digits here in this order. So if you know what 1/7 is, and you know that 2/7 is about that, so it's got to be the one that's about 0.28. 3/7 is going to be about 0.28 plus 0.14, about 42. So 3/7 is 428,571 repeating, and so on. So, but anyway, we do see that the second lowest number and the second highest number are our quartiles. So let's jump back over to Excel. So I see that Q1 is the second lowest number and Q3 the second highest. And IQR is the difference of those. And in this case, I'll just put the 1.5 directly in L and U. So I want for the lower bound Q1 minus 1.5 IQRs. For my upper bound, Q3 plus 1.5 IQRs. And I see I get a lower bound and an upper bound of 110 and 766. My IQR method is actually even a little more generous than my 2 standard deviation method in this case. And I see I still get no outliers. I get no outliers from either of these. I get a mid-range that is really not substantially bigger than the mean. I'm probably going to think that this isn't really a skewed data set. I'm going to think that this Pearson coefficient is leading me down the wrong path. Maybe it's just because I have a fairly small data set to deal with. And I'm going to say that I don't think there's evidence of skewedness because we don't have outliers. These two measures of center don't seem to line up the right way. So I think probably lack of evidence of skewedness and no outliers. Okay, so that wraps us up for the chapter 3 material. And then just let me redo my share here. And we'll move on to the chapter 4 PowerPoint. The chapter 4 PowerPoint, I handed out the slides in class and they're also up on Blackboard. Okay, so we started talking about probability in class. I'm not going to rehash that, but just really quickly, the perspective is changing between chapters 2 and 3 and chapter 4, and really chapters 4 through 6. Chapters 2 and 3, we basically said we don't have all the information about the thing we're interested in. We're typically thinking that we're interested in the population, but we have access to a sample. We compute some statistics about the sample, and we try to use that information to infer something about the population, about the underlying structure. Chapters 4 through 6, this idea of probability is a mathematical model where essentially we're saying that we understand everything there is to know about the structure. We understand the frequency distribution of what the population looks like, essentially. And we're trying to guess what will happen on an individual instance of this experiment, an individual, say, roll of a 6-sided die or an individual flip of a coin. So we're trying to say, what do I think a typical result of such a probability experiment will be, or what do I think a reasonable range of results of such a probability experiment might be. We have some terminology. An outcome is the result of a single trial of a probability experiment. The sample space is the set of all possible outcomes of a probability experiment. And when we say all possible here, we do mean all possible. Keep in mind, this is a mathematical model, so we are setting the rules. So if I say in my model, when you roll a die, it comes up 1, 2, 3, 4, 5, 6, nothing else is possible. Those are the rules. Now you might say, when we try to overlay that model into reality, maybe there are things that could happen to the die. Say it lands on an edge or something. That's not covered by the model. But in terms of the model, we can enumerate all possible outcomes. And an event consists of a set of outcomes. An event could have no outcomes in it. It could have all of the outcomes. But typically our events, or interesting events anyway, have some but not all of the outcomes. So some examples. Probability experiment, rolling a die. Anytime that we say a die, we mean a standard 6-sided die where all faces are equally likely. If we say flip a coin, unless otherwise noted, we mean a fair coin, so heads, tails, each come up equally likely. And let's say the outcome that we're interested in is just the number we get when we roll a die one time. The sample space under our model is 1, 2, 3, 4, 5, 6. These are the possible outcomes. And some events, there's lots of events we could talk about, but we could talk about events like, say, rolling an odd number. This would be an event consisting of the outcomes 1, 3, and 5, and not including the outcomes 2, 4, 6. We could talk about an event rolling a number greater than 2. We have to be careful here. Greater than doesn't include 2. So this event rolling a number greater than 2 would include the outcomes 3, 4, 5, 6, and would not include 1 or 2. Now, if it was rolling a number greater than or equal to 2, then that event would include 2, 3, 4, 5, 6, would not include 1. So we have to be careful with the wording in these. We could talk about an event that's kind of phrased in the negative way, something like not rolling a 3. That event would contain the outcomes 1, 2, 4, 5, 6, would not contain 3. Another example of a probability experiment, rolling a die 2 times. And the outcome being the numbers in order that we get when we roll the die 2 times. So our sample space looks something like 1, 1. This isn't an 11. It's 1, 1 signifying 1 in the first row, 1 in the second row. 1, 2, 1, 3, 2, 1, 2, 2, etc. And some possible events could be something like rolling 2 odd numbers. This would include outcomes like 1, 1, 1, 3, 1, 5, would not include outcomes like 1, 2, or 2, 4. An event could be rolling a number greater than 2, kind of on either of our rolls. So an outcome like 1, 4 or like 5, 6 would be in that event, but an outcome like 1, 1 would not be in that event. We could have an event phrased in the negative just like before, say something like not rolling a 3 on either roll. So 1, 1, 1, 2, etc. are outcomes in the event, but an outcome like 1, 3 or 3, 3 would not be in the event. We could consider a fair coin. We flip a coin, it comes up heads or tails. What about the experiment flipping a coin 5 times? The outcome here might be the sequence of heads and tails. So I flip the coin once, I write down heads or tails, I flip it again, write down heads or tails, and that sequence. So something like heads, 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 tails means the first 4 flips were heads and the last was tails. Whereas heads, 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 tails, heads means that the 4th flip is the one that was tails. And we could go through and enumerate all these. If we're going to enumerate these, we want to do it systematically. So we might say start with the all heads sequence. And then we say, well, okay, there are some sequences with 1 tail. Where could that tail end up? It could end up in the 5th place, or the 4th place, or the 3rd, or the 2nd, or the 1st. And we could then say for 2 tails, what happens? For 3 tails, what happens? 4 tails, what happens? And then 5 tails is, of course, just the sequence with 5 tails. So if we were going to try to enumerate all of these, this would take a while. I'm not going to write them all out, but we would want to go through systematically so that we don't, accidentally double count any or miss any. Some events might be something like flipping all heads or getting no tails. We could say it kind of either way. That would be the single outcome with 5 heads. We could say an event flipping 3 heads, then 2 tails. That would be the single outcome, heads, 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 tails, tails. But we alternatively could talk about the event flipping 3 heads and 2 tails on 5 flips. Again, subtle difference in the language here, then versus and. When we just have and, we just need 3 heads and 2 tails on 5 flips. The ordering doesn't matter. So 3 heads, then 2 tails counts, but also heads, heads, tails counts, or there's a bunch of others that count. Any of these that would fall into this line here would be outcomes that count. They have 2 tails and therefore 3 heads. So the idea of classical probability is really what we're working with here. Classical probability uses sample spaces, this mathematical structure, to determine the probability that an event will happen. Really kind of what we're thinking about when we, under classical probability, say the probability of an event is something is 20% or whatever. What we're kind of imagining we're doing is, let's say that we're making a statement about die rolls. We're imagining we run that experiment and we run it again and again. We run an identical experiment, say 1,000 times, 10,000 times, something like that. We count the number of results from that experiment that are in our event, and we divide that number by the total number of times we ran that experiment. So kind of the number of successes over the number of tries, and success being that we got a result from the experiment that's in our event. And that ratio is what we expect this idea of probability to model, right? If we rolled the die, if we ran the experiment 10,000 times, we'd have a very large sample, and we could evaluate the sample proportion of success, the sample proportion of times that we were in that event. And this idea of probability under classical probability is what we would expect that sample proportion to be estimating. This classical probability would be the population parameter for that sample proportion. So computing probability, this is how we compute it. The probability of an event is computed as the number of outcomes in the event divided by the total number of outcomes in the sample space, under the huge caveat that we assume that all outcomes are equally likely. So in chapter 4, we sometimes have to take great care in setting up our sample space, our set of all possible outcomes, in such a way that it makes all of the outcomes equally likely. But note that this is pretty clearly what we would be estimating by that process of running the experiment a whole bunch of times and figuring out which proportion of those outcomes is in the event. Okay. So let's look at, for example, the probability of rolling an odd number is 1/2. I think that's pretty obvious, just kind of as a general statement. But let's see if we can use the terminology and the computation to actually show that. So we note that our sample space is 1, 2, 3, 4, 5, 6. And these are all equally likely. That's just kind of the assumption of a fair six-sided die. Rolling an odd number, that event consists of 3 outcomes, 1, 3, 5. So what's the probability we roll an odd number? That's the probability that we get an outcome that's in the event, 1, 3, 5. Well, there are 3 outcomes in that event divided by 6 outcomes in the sample space, 3, 6, 1/2, or 50% for the probability. That's exactly what we expect. So let's look at another example. What if we were looking at flipping a coin and we wanted to know what's the probability that we flip a head, then a tail in 2 flips of a fair coin? Here we have to be a little careful with our sample space. We don't want to make a sample space like this, where we might be thinking of this as getting 2 heads, getting 1 head, or getting 0 heads. The reason is that for the first flip, we could get a head or a tail. For the second flip, we could get a head or a tail. So we really have 4 equally likely outcomes here. So I noticed that tail head and head tail kind of should be counted separately. If I were to combine them under this, say just getting 1 head and getting 1 tail, this outcome would actually be twice as likely as either of these. So again, I have to be careful when I set up my sample space to make sure that I'm describing outcomes in a way that they are equally likely. So I have to have head tail and tail head as separate outcomes. Flipping a head then a tail, there's only one outcome in that event, head tail. There are 4 outcomes in the sample space. They are all equally likely. So the probability of getting head then a tail is 25%. 1 in 4. So what about 2 rolls of a dice? Or 2 rolls of a die, 2 dice being rolled? Same kind of setup, right? We don't want to just say, getting a 2 and a 3, or even worse, like getting a sum of 5 or something like that. We need to say what happens on the first roll and on the second roll. And we note that when we divide this up, we get a 6x6 grid. There are 36 outcomes in the sample space, and they look like, for instance, 1, 1, 2, 1, 3, 1, 1, 2. So 2, 1 is different than 1, 2, right? So when I'm enumerating my sample space, I want to note that. I know rolling a 2 then a 3 means I got a 2 on the first roll, a 3 on the second roll. There's only one way to get that. I have to get a 2 then a 3. That's the only way. So 2, 3 is the only outcome in the event. So there's one outcome in the event divided by 36 in the sample space, again, all equally likely. So our probability is 1/36, or about 2.8%. If I had instead asked, what's the probability of rolling a 2 and a 3 in 2 rolls? So getting a 2 and also getting a 3 in 2 rolls, there's 2 ways that could happen. I could get a 2 then a 3, or I could get a 3 then a 2. So in this case, the probability of the event, there's 2 outcomes in the event, 2, 3, as well as 3, 2. Still 36 outcomes in the sample space, same sample space as before, we just changed the event. So 2/36 is about 5.6%. So again, be careful with the exact wording of events or of the setups of problems. So in a normal deck of cards, what's the probability of drawing a jack or higher? So a quick diversion over here to decks of cards. These come up sometimes in these probability calculations. So I know that not everybody has the same familiarity with these. So let's just discuss really quickly what a deck of cards is. A deck of cards consists of 52 unique cards. And each card has 2 characteristics. It has a suit, hearts, diamonds, spades, or clubs. Hearts and diamonds are considered red cards. Spades and clubs are considered black cards. It also has a value. And these values are the numbers 2 through 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. The face cards, Jack, Queen, and King. And then the ace. In some circumstances, ace is counted as a 1. But most of the time in things like poker and so on, the more familiar games, ace is often counted as being a high card. So I've listed these in increasing value. So we consider an 8 to be a higher value than a 2, of course, but we consider, say, a jack to be a higher value than any of the number cards 2 through 10. Queen's better than jack, king is better than queen, and quite often ace is the kind of highest value card. Again, it depends maybe on the game you're playing or on the particular house rules of that game or something, but for our purposes, we'll consider ace to be a high card. So if you want to see what the cards look like, you can, of course, Google deck of cards or something like that. Decks of cards also maybe sometimes have jokers. We're not including jokers in the kind of standard deck of cards. So each card has these 2 characteristics, and each one is unique. So we have hearts, diamonds, spades, and clubs for the suit, and we have 2 through 10. Jack, queen, king, and ace. Running out of room here at the bottom for the values. So we see, for instance, we have a 2 of hearts. We have a, 3 of spades, and so on. There's exactly one of each of these different value suit combinations. We have 13 rows, 4 columns, 13 times 4 gives me 52. Okay, so now that that's out of the way, as an aside, for things like decks of cards, for those kind of problems, they won't be on the exams. You might see them on the homework, but you can, either refer back to this or, Google decks of cards or something if it's unclear. If you're unclear exactly what the different suits or values or something are, but they won't be on something like an exam. Okay, so what's the probability of drawing a jack or higher? There are 52 cards, all equally likely to be drawn. And the cards that are in the event are any of these 4 values, jack, queen, king, or ace, and any of the 4 suits, hearts, diamonds, spades, or clubs. So in other words, these are the outcomes in the event. 16 outcomes in the event divided by 52 total outcomes in the sample space, total cards in the deck. So 16 out of 52 is 30.8%. Note that we could also use a symmetry argument here. Sometimes this can be helpful in probability calculations. We note that as far as values are concerned, the deck really just contains 4 identical copies of the values 2 through 10, jack, queen, king, ace, if we're only concerned with values. So in other words, there's 4 2s, there's 4 10s, there's 4 kings, and so on. Well, I could just look at a single one of these, and I could treat it individually. I could say, what's the probability of getting a jack or higher? There are 4 ways to get that, 4 values, jack, queen, king, and ace, out of 13 possible values. And 4/13 is the same as 16 out of 52, right? Just divide a factor of 4 out of top and bottom. So we can use this symmetry, this fact that as far as just the values are concerned, there's essentially 4 copies of the deck, 4 copies of the values 2 through ace that are in the entire deck. So sometimes that can be a helpful strategy in probability problems, taking advantage of something like a symmetry like that. Okay, so some probability rules. These are rules or properties. These are things that are always true about probabilities. Probabilities are always between 0 and 1, inclusive. So this is clear from the calculation, right? So why is the probability non-negative? Why does that have to be bigger than or equal to 0? Well, probability of event is number outcomes in the event over number in the sample space. But of course, number of outcomes in the event, the least number of outcomes I can have in the event is none. The event can contain no outcomes, but I can't have like -2 outcomes in the event. So this has to be a number bigger than or equal to 0. Number of outcomes in the sample space is a positive number. So this has to be non-negative. Probability of event less than or equal to 1 might be a little less clear why that ought to be true. But again, probability of an event is number of outcomes in the event over number of outcomes in the sample space. But remember that the sample space, by definition, contains all possible outcomes. In other words, there can never be an outcome in the event that is not in the sample space. Or in other words, the most number of outcomes I can have in the event is all of the outcomes in the sample space. So the biggest this number could be is 1. The most full my event could be is if it has all of the outcomes in the sample space. It can't have any more, because if it had more outcomes than in the sample space wouldn't contain all possible outcomes. So my probabilities are between 0 and 1 inclusive. This is a helpful check. If you go through a problem and you get to the end and you're claiming that the probability is 125%, or that the probability is negative 30%, something went wrong. So go back and check your work. If an event cannot occur, if it's impossible, then its probability is 0. So we're making a claim here that the idea of impossibility and probability of 0 are essentially the same thing. So let's see what that means. If an event cannot occur, if E is impossible, what does that mean? That means there are no outcomes in the event. If there was even one outcome in the event, then I could end up with that outcome from my probability experiment. My event would be possible. So if the event's impossible, there are no outcomes in the event. But then the probability of the event is number of outcomes in the event is 0 over whatever number in the sample space is 0. So if an event's impossible, its probability is 0. If an event's probability is 0, the only way the probability can be 0, I have some number, let's call it K, of outcomes in my sample space. The only way my probability of the event can actually be 0, not saying rounded to 0, not saying it's pretty small and we just rounded it to 0, but the only way it can be actually 0 is to get an actual 0 on top here. But the 0 on top there is counting the number of outcomes in the event. So that means there must be 0 outcomes in the event. It means that it must be impossible to achieve that event from this probability experiment. So as a side note, if I had, let's say, a probability of some event was like 1 in 10,000, I really wouldn't want to round this to 0, because probability being 0 means kind of a very specific thing. It means it's impossible. If I was going to write this, I would probably say something like probability of event is 0 plus, indicating that it's a very small probability. It's extremely unlikely to happen, but it is possible. And I would write this as 0 plus to distinguish it from a probability that's actually 0, where it's literally impossible, where there are no events, or sorry, no outcomes in that event. This is kind of why we, like, morally speaking, don't want to talk about percentiles from section 3.3 that are 0, something that the 0th percentile or the 100th percentile is just kind of, bad form in this sense. One little side note is this idea here presumes that we have a sample space where the outcomes can be enumerated, or we have a sample space with a finite number of outcomes. Hypothetically, if we were to have a sample space with an infinite number of outcomes, if we got something like 10 over infinity, this is 0. So if we have an infinite number of outcomes, this discussion becomes a little more nuanced. For right now, we're not thinking about that. But when we get to things like continuous probability distributions in chapter 6, this idea that we're talking about right now becomes a little more nuanced. We can say a similar thing about probability 1 events. If an event is certain, if it definitely will happen, if it is guaranteed to happen, then its probability is 1. So if you want a little bit of practice, go back through this line of logic, argue that if an event must occur, then its probability must be 1, and argue that if the probability is 1 exactly, then the event must occur. Note that if the probability is just about 1, I would write, when I round it, I'd write 1 minus, indicating that it's nearly certain to happen, but it is possible for it not to happen. I wouldn't want to round my probability if it was like 999 out of 1,000. I wouldn't want to round that to 1 or 100%. I would probably include this little superscript here just to note that it's a little below 1. That for all intents and purposes, it's about 1, but that's not saying that it's a certainty. And then lastly, the sum of the probabilities of all the outcomes in the sample space must equal 1. In other words, if I made a whole bunch of events, each of which contains exactly 1 outcome from the sample space, and I have all of these outcomes represented in one of these events, and if I compute the probability of each of those events, each holding just a single outcome, and I add those probabilities together, that has to equal 1. In other words, what we're saying here is if I run the probability experiment, something has to happen. With certainty, 100% of the time, if I run the probability experiment, I end up with an outcome that's in the sample space. That's basically by definition of the sample space. It's the set of all possible outcomes from the experiment. Okay, so again, what are we kind of thinking about when we are thinking about a probability? We're imagining this idea of, say, rolling this die or flipping this coin or something, running this probability experiment 1,000 times, 10,000 times, a whole bunch of times, counting the number of results that satisfied the criteria for the event, dividing that number by the number of attempts we made, and looking at that ratio. And that's really what we would call empirical probability. So if I was interested in the event that, say a random person chosen from the population of Pittsburgh is taller than 6 feet tall, one way of evaluating that, the probability of that event, is to suppose that I have a model and that I know, all there is to know about the heights of people in Pittsburgh. And then I could ask what happens if I draw one random person, what's the chance that they're taller than 6 feet tall, something like that. But the other approach I could take is I could say, well, I really don't know that answer, but maybe what I have access to is a sample. Maybe I have a sample of 100 Pittsburghers' heights, and I can look at that sample, and I can go through, and for each one of those observations, for each one of those people, I can say, is their height greater than 6 feet tall or not? I can count the number that are greater than 6 feet tall, divide that by 100, and maybe I think that that would be an estimate of the true probability that a Pittsburgher is taller than 6 feet tall. So that's the idea here of empirical probability. So it's taking this classical probability idea, but it's thinking of it from the perspective of kind of the chapter 2 and chapter 3 material. In other words, another way of thinking about it is I can take my raw data, I can massage my data into a frequency distribution, and then the probability for a class can be estimated by the frequency for that class divided by the sample size. And I think the last thing we'll talk about today is the law of large numbers. So this is my joke for law of large numbers. So a fun little quote from Sherlock Holmes from the book The Sign of Four, where he talks about kind of an individual person. An individual person is an insoluble puzzle, but averages may remain constant. So the law of large numbers, roughly speaking, says that for a sufficiently large sample size, the frequency distribution we guess when using empirical probability, when taking the sample, putting it into a frequency distribution, and estimating the probability that way for each of the classes, will be close to the actual underlying frequency distribution, the actual underlying probability of each of those classes from classical probability. So if I construct a relative frequency distribution based on a sample, those percentages should be estimates of the probability of each of those classes under classical probability. Very important, what the law of large numbers does not say is something like this. It does not say something like, well, I know that if I say flip a fair coin, I should get about 50% heads and 50% tails. So if I flip a fair coin and I start flipping and the first 10 flips all come up heads, I should not say, well, I think tails is due, right? Because we've had a bunch of heads. So something, like God needs to be sitting up there and like balancing things out or something like that, we got 10 heads in a row. Well, we got to start getting tails to make sure that things balance out or otherwise, something, in the universe will blow up or something. That's not what it's saying. Really so this is sometimes called the gambler's fallacy. But really what the law of large numbers is saying is, well, okay, you got 10 heads in a row. That's kind of a strange event to happen, I suppose, under a fair coin. But if you keep flipping that coin long enough, if you collect a large sample, say 10,000 flips, 10 million flips, you're probably going to see a sequence of 10 tails in a row somewhere that'll kind of balance that out eventually. So that's really what the law of large numbers is kind of saying. We have a couple of theorems that we've talked about, and we'll really dig a little deeper into these theorems at the end of, I guess really at the end of chapter 5 is probably when we'll go through the proofs of these, just so we can kind of knock them all out at once. But the law of large numbers, we will discuss this, the proof of this as well. We can actually more or less prove this carefully. So we'll state it carefully, we'll prove it carefully. But for right now, we're just thinking of the law of large numbers as saying that the kind of chapter 2 idea of a relative frequency distribution is inherently linked to this chapter 4 idea of probability of an event. So the relative frequency of a class is an estimator of the probability of that event that's that class. And then, so I like this quote from Nassim Taleb. He was a hedge fund manager and made a whole bunch of money in hedge funds, and he wrote a book called The Black Swan. He's written a couple other books. The Black Swan has nothing to do with the ballet movie that came out some years ago. But one of his quotes is that the minds of the gods cannot be read just by watching their deeds. So that's kind of what we're suggesting here, right? Is that by just taking a big sample and getting a relative frequency distribution, we can infer something about the underlying structure of the whole thing. And Taleb is kind of arguing maybe against thinking like that too rigidly. And really where Taleb made his money is in buying options, so a type of investment that basically just pays off whenever a certain event happens. Say whenever a certain stock gets above a certain value or below a certain value, something like that, then the option pays off. Otherwise, it doesn't. And what he would do is he would go and buy options that would only pay off under events that basically people thought were impossible to happen. And he would buy these options, and most of the time he would lose his money. But people would sell these because they just said, oh, that's impossible to happen, or it's effectively impossible. They would sell them to him for dirt cheap. They didn't care whether he was paying $100 for the contract or $200 for the contract, because it was just basically free money to them from their perspective. But every once in a while, he would, that kind of quote impossible event would occur, and he would, make a huge amount of money on a very small percentage of his investments, and he would lose a very small amount of money on the vast majority of his investments. And he was able to estimate that tail risk, the likelihood of those very rare events occurring, better than other people could. So these people were saying, oh yeah, I don't really care what I charge you for that contract because it's effectively free money. And he looked at it and said, oh, you're undercharging for that, so that's a good buy for me. Even though it probably still won't pay off, kind of on average, I think it will. And when I hit it big on one of these, that'll be more than enough to pay off all of my losses. So I think that idea is important because maybe estimating the probabilities of events that are likely to occur, we might be able to do that with a reasonable sample size. But if we have a type of event that if we had complete knowledge of the entire structure, we might say, oh, that kind of event only happens 1 in a million times or 1 in 10 million times. But when it does happen, it's extremely important. It's, disastrous or hugely beneficial or something like that. Well, if I just collect a sample of size 1,000, do you think I'm going to have enough data there to tease out what is likely to happen 1 in a million times or even 1 in 100,000 times? Yeah, almost certainly not. I'll be able to estimate the probabilities of the commonly occurring things, the things that happen 20% of the time. I'll be able to estimate those very well because I have good coverage for things that happen 1 out of 5 times. I have maybe 200-ish occurrences of that in 1,000 data points. But for something that happens 1 in a million times, I would need, a sample that's 1,000 times bigger or 10,000 times bigger or something to be at all confident that I would see such an event. So that's the huge caveat of the law of large numbers is this: for a sufficiently large sample size. The mathematical theorem says that this idea is true in the limit as n goes to infinity, as the sample size goes to infinity. But practically speaking, of course, we're never dealing with infinitely large samples. So practically speaking, what's a big enough sample size that we're confident that the frequency distribution we guess is close to the actual underlying distribution? That is not an easy question to answer. So I think that's where we'll leave it off. When we come back on Tuesday in class, we'll pick up here talking about subjective probability and finish up the first PowerPoint for chapter 4 and then move on to the second. All right, that wraps us up for today.